Our next speaker is Professor Peter Venn. He is from Department of Theoretical Physics at the Wigner Research Center for Physics and Department of Theory, not theology, theory. Emergent, his talk is titled Emergent or Fundamental about the Origin of Thermodynamic Universality. Professor Peter.
Do you hear me? Is it okay?
Yes, we hear you.
So, yes, thank you very much. And greetings to everybody, ladies and gentlemen. I will speak about the physical background. So I will speak about physics. I see a kind of ecological niche in the previous speaker's talk. So Adrian didn't show any formulas. I will contribute from this direction. So my talk is about universality, and as it is understood from the point of view of thermodynamics. First, the classical question of universal temperature, then the evolution equation, how much they are universal, then a classical question of gravitation from this point of view, and finally, what could we, let's say, understand from the modern developments of non-equilibrium thermodynamics when we approach from this point of view. Okay, first vocabulary. In the title, there was the word emergent. I understand that it follows from substructural microscopic properties. The word universal will be used as independent of the microscopic or mesoscopic material substructure, a kind of contrary of emergent. And finally, please don't mix evolution in any kind of biological material or process. Evolution equation in this talk will be about dynamic equation of motion, so especially a partial differential equation that determines the time and position dependence of the field, of a field. So let's a little bit recall what kind of universalities we encounter. For example, the classical universality of temperature. From an empirical point of view, we measure temperature in many materials. Also, please recall that balances and conservation laws are universal in a more or less similar sense. A specific aspect is gravitation, especially the weak equivalence principle, which says that the inertial and gravitational mass are proportional, and this is independent of the material. And also there are some suspected gas universalities, which is described by the kind of universal evolution of slow dynamics and phase fields. And especially, we should recall that second law is expected to be a universal principle. Okay, let's start with universal temperature and recall the classical argument of Lord Kelvin. It starts from the Kelvin-Planck formulation of the second law. It says that there is no way to construct the cyclic operating machine device that extracts heat from a single heat bath and performs work. This is this perpetuum mobile of second kind represented in this figure. Then the argument continues that the heat engine looks like this way, by the way, and this absorbs and emits heat and performs work. And the reversible device is the most effective. It is easy to see because if I have a higher efficiency than a reversible one for a particular device, then I apply a reversible one as a refrigerator and construct a machine, a perpetuum mobile of second kind, just equilibrating the absorbed and emitted heat in the figure. And the extra work will give the perpetuum mobile of second kind. The argumentation continues that the efficiency depends only on the reservoir of the temperature, on the reservoir temperatures, and then just using two machines and considering it as a single one get the following functional relation, and the solution is a factorization of the efficiency by the temperature, and we introduce a temperature with this factorization function. And this is the universal temperature as it is constructed by Lord Kelvin. please observe, the conditions are the reversible process and the Kelvin-Planck formulation of the second law. In this sense, the universality is originated in the universal conditions. Also, there are some observations are important. So the Kelvin-Planck form of the second law states an existence of entropy as a thermodynamic potential. This is the consequence of that. It is loosely formulated, but when want to give a little bit mathematically analyzed, then we can understand that. So what follows is the existence of thermodynamic potential as a universal consequence. Also, it is important that this form is not related to the Clausius form, not related to increasing entropy. There are we don't speak about real processes here. And especially problematic is the concept of reversible process. And also there are some other comments and complications that can be considered. For example, this is actually Carnot engine, but not usual Carnot engine with a deeper analysis, because, for example, the Curzon-Albor one is a Carnot engine in this sense, what I have shown there. And also, the interpretation of the process, that is a remark already, it can be made exactly. And the whole argumentation is independent of that. The temporal thermodynamics is possible, however, we lose universality here. And the final comment, which is always a question, that statistical physics cannot give a proof of universality or general principles, but can falsify. And if a concept is universal, then any demonstration is representative. That's all about, let's say, recalling the universal temperature. How is it interpreted in thermodynamics? The next point is the universal evolution. Let me start with the Fourier equation. Classical irreversible thermodynamics derives the Fourier equation with the following procedure. We assume as a condition the balance of the internal energy, this formula, this is a so-called substantial balance form, and we assume thermostatics. We assume that there is an entropy function that depends on the internal energy, which is actually trivial here in one variable. But using thermostatic information and the constraint, we calculate the entropy production, the entropy balance in this form, and obtain the entropy production formula. And classical irreversible thermodynamics says that there is a solution of this inequality. We assume that the heat flux is proportional to the gradient of the reciprocal temperature with a non-negative coefficient. What is the background of this formula? There are some general aspects and the material aspects. We use space-time, non-relativistic space-time, of course. We assume the existence of entropy, as I mentioned, and assume the second law, the increasing entropy, the entropy inequality. And the material aspects are separated. Let's see somehow the space-time aspects. Why does it necessary in an argumentation speaking about universality? Here you see the substantial form of the balance is the consequence of the so-called local form. So this is a transformation from an external laboratory observer to the co-moving observer. Co-moving observer means that we are removing the laboratory related concepts and we can construct real material related functions. There are several particular aspects here how to do it. One important point that the internal energy itself is a transformation of the energy, which consider the energy which is material related from the point of view of movement. Also, when we survey the mentioned thermodynamical aspect, I already emphasized that the existence of thermodynamic potential comes from the Kelvin-Planck statement, but also here the extensivity is also introduced because field theory, we need this kind of scaling property that small is similar to large. And these kind of assumptions are conditions, are aspects of universality. And also my last comment here is that it is not really a heuristic argument. It could be made more rigorous. Anybody who is interested in more mathematical details can find that several parts can be, let's say, formulated with strict logical consequences of the conditional inequality when the balance of the internal energy is introduced properly and the proper functional relations are really considered. Okay, again, we have the Fourier equation. When we substitute Fourier law into the energy balance, we obtain that. And it has clearly some material dependent part, the specific heat and the heat conduction coefficient, and material independent part, universal part. Of course, the choice of fields is a material dependent part from the point of view of space-time. Surely we cannot use tensorial representation, I mean second order tensor in heat conduction. This is the choice of the material or the phenomena. And the whole process is actually separates the two parts, and what is universal part, this is, so in a sense how it is, and in the conditions how the introduced universally, then the consequences are universal. Okay, as a summary here. So general conditions lead to general consequences. This is the trivial statements, and the whole procedure of non-equilibrium thermodynamics here is a separation of universal and material dependent parts in the thermostatic and in the continuum levels. And of course, the level of universality comes from the specific particular conditions of what we applied. Also, again, I would like to emphasize.
The target has been delivered. The target order has been delivered.
I don't understand. I'm sorry. Do you hear me still?
Yes, Professor Peter, go ahead.
I'm sorry, okay. So my next point is that this is, in the previous example, in the Fourier equation, the balance of internal energy was an important part of the evolution. Only the constitutive equation, the Fourier law, was constructed. However, modern thermodynamics actually can construct evolution equations from pure thermodynamic principles, and this is one of the main directions where the various theories are evolving. For example, we can extend the heat conduction introducing additional variables and keeping the compatibility with kinetic theory. The argument here is that extending the state space, for example, with the heat flux, this is a quadratic contribution here. We can calculate the entropy production, and obtaining the particular part of the entropy production, we construct also, again, a solution. And in this case, you see Q is proportional to the formula in the parentheses. And we can get from thermodynamic argument a balance form equation for the entropy flux with a particular source term. And the second law requires that L should be non-negative. And if we eliminate Q and B, it is possible, then we can understand that the whole process is actually introduces inertial effects and reproduces several well-known heat conduction equations, more or less confirmed experimentally or theoretically predicted. Then you see, again, this procedure, I applied the same kind of construction with some new contributions. Contribution was the quadratic entropy. And as long as the microscopic theories, let's say, preserve this property, the quadratic entropy, by the way, this is the kinetic theory calculation result in a sense, then the universality is preserved in the same sense as in case of Fourier equation. Whether Q is objective and in what sense, this is another question. It is more technical, but also should be considered properly. Then the question of universal gravitation. We know well that there is a timeline of that. The weak equivalence principle, or the universality of free fall, as I mentioned, the ratio of gravitation inertial mass was measured by Newton first, and then it serves as an empirical foundation of general relativity, experimentally checked by torsion balance experiments of Utwish. The most recent refined experiment is the satellite microscope experiments, and one can find more material about the word fifth force, because the existence of fifth force could be a violation of the weak equivalence principle. So in gravity, the universality plays a very important role in a particular sense. Also, there are theoretical connections. For example, all black holes are the same or similar, which is the consequence of no-hair theorem. So therefore, they are in this sense universal. And also, in the last decade, there is decades maybe, more and more intense discussion about the thermodynamic origin of gravitation. And this is where they use the word emergent. Emergent because it has thermodynamic origin, therefore we can put or we can imagine some microscopic background in this case. However, if it is emergent, then why it is universal? This is a question. Also, one final remark, that up to now I have constructed pure thermodynamic, pure dissipative evolution equations. Both Fourier and the mentioned equations are pure dissipative. And one of the important arguments against the thermodynamic origin of gravitation is that Newtonian gravity is non-dissipative, therefore it cannot be reproduced from thermodynamic reasoning. Okay, let us shortly survey a construction which follows the same rules or same structure as previously mentioned. We assume or introduce an entropy function, which is a fluid entropy, extended, I mean, introduce some scalar variable, and also the gradient of the variable is a part of the variable in the thermodynamic potential. And it is introduced in a very particular form. So the scalar variable is energy, and actually this is the potential energy of gravity, it will be. And the field energy is also introduced here. So the square gradient is not an accidental contribution, and not only the simplest contribution that one can put into this system, but also well known in gravity theory. Then applying the same argumentation and little calculations, so calculating the entropy inequality using the balance of mass, momentum, and internal energy as constraints, we can obtain the following entropy production. With the previously introduced thermal part, it is not mentioned, but this is the mechanical part. So this is a traditional mechanical interaction. For example, viscosity follows from that with the same linearization argument of the entropy production. And an additional contribution, and if we assume that gravity is non-dissipative, then we should assume also that the expression in the parentheses, the blue one, the Poisson equation, is fulfilled. So it is zero. So without dissipation, it is a perfect fluid, and Newtonian gravity, in a sense, follows. What is important here, that dissipative and non-dissipative effects can be constructed by thermodynamic arguments without variational principles. And the same kind of universality arguments also apply. What I have introduced here, the particular form of the extending the thermodynamic state space and especially the field energy, those are the conditions. And what about equivalence principle? Here, the red row represents the gravitational mass. When one surveys the derivation, one can find that the gravitational mass actually this one. So this is the thermodynamic mass, and it must be equal or proportional to the inertial mass, which is actually the multiplier of the acceleration in the momentum balance. And those are the same. Those are the same if we are speaking about the same fluid, or at least this is how it appears in this thermodynamic argument. Okay, these are somehow that the universality argument can be extended from thermostatics and from thermostatics to thermodynamics, and the theories of non-equilibrium thermodynamics are actually consider or at least react in this direction. Of course, there are many. So you see this topical issue of philosophical transactions of the Royal Society. There are many details, and you can find these many, I would say, the important theories of non-equilibrium thermodynamics. For example, general equation of non-equilibrium reversible, irreversible coupling, or rational extended thermodynamics, or or also the method of steepest entropy ascent. Some of the some representatives of these theories will appear also in this conference. And for an outsider, the question arises that why so many, how to decide, why there is no single theory of theoretical approach of thermodynamics, and how, why, for example, one doesn't apply Occam's razor. Actually, it is not so easy to choose the simplest one. So Occam's razor is a dangerous device. In a many dimensional decision space, it is not easy to find a good optimization criteria. Why? Because these theories are considering different conceptual benchmarks, different compatibility benchmarks, and use different methodologies. And all these can be, how to say, weighted differently in the various approaches. For example, from a universality point of view, the conceptual benchmarks are the most important. Variational principles, for example, are related differently and quite in the various approaches. Some of them introduce as a given, so introduce in, so somehow embedded in the theory, so they are built in. Some theories are reproduce variational like equations, and some of them simply don't care. I mean, only deal with the parabolic structure and don't introduce any modified or original Hamiltonian principles. Also, a conceptual benchmark is space-time. Some methodologies exclude use, for example, relativistic space-time arguments. And also dissipative and non-dissipative evolution is treated differently. Somehow, if these conceptual benchmarks can be addressed together, then we can understand more or better the concept of universality. The compatibility and let's say...
You have 5 minutes.
5 minutes, okay.
Yes.
So the compatibility benchmarks also very diverse. So those theories that are good in continuum mechanics not necessarily can reproduce kinetic theory. Therefore, universality arguments also important here, because I think that the uniform thermodynamic approach could explain all these particular areas and somehow address the important challenges. And finally, the methodological preferences, so the particular assumptions, starting axioms of the various approaches can be really different. And here I would mention first on only the symmetric hyperbolic structure, where thermodynamics can reproduce this symmetric hyperbolic structure, because assuming a thermodynamic potential and transforming a proper, for example, to the entropic intensive variables, the corresponding equations are automatically symmetric hyperbolic by construction. So this is a very attractive property, mathematical property, but also from a physical point of view is well motivated. And it is a question whether is it the primary aim in a theory construction or could be considered as a secondary problem. And the mentioned theories are also different in this respect. So I have a little bit outlined what is going on in non-equilibrium thermodynamics. So you have seen that there are many branches. There are collaborations, discussions, and also battles. And why they are considered as non-equilibrium thermodynamics is that they have a common agreement among the various branches that the second law is fundamental. And also there is a common feeling that if there is a system, so there is a structure with common structural elements, then there is a predictive power to in various and really different areas of physics and chemistry and biology and so on. And also there is a common feeling that the universality, more or less in the same sense that I've mentioned, I tried to argue previously, that the seamless application of general principles can lead to a kind of substructure compatibility when the microscopic theories will be representative. And finally, there is a common dream whether we can construct really a universal, uniform, common theory and whether we can understand somehow the common structure of these various branches more deeply. So actually, that's all what I wanted to say. Finally, some final words. So this is reality, let's say. This is a representation of science. Science produces models that are simplifications of reality. And this is thermodynamics, a particular projection device where, from the point of view of universality, the outline of the models became clearer. And in this sense, thermodynamics could be the essence. Thank you for your attention.
Thank you very much, Professor Witten. Now, our first question is coming from Lib Tims. Lib, are you?
Hi, how are you doing?
Okay.
Can everybody hear me?
Yes.
Yeah. Yes, Peter, just a general question. On your overview of your talk, you say that your approach is to use non-equilibrium thermodynamics to derive evolution equations of dissipative systems.
Yep.
So,
and dissipative too, actually.
So a lot of people who believe in the work of Ilya Prigozhin say that societies are dissipative systems. So is one of your equations meant to model evolution of societies as dissipative systems from your talk?
My point was strictly physics. So this is an investigation related to theories of physics where dissipation also important. I don't exclude, moreover, I believe that non-equilibrium thermodynamics could be used to describe society. Actually, several economic theories are, how to say, well elaborated that it could be done, but I don't know. So I'm not a specialist of that.
Okay.
Okay, the second question is coming from Shebnam Musavi. Shebnam, are you online?
I'm here, yes, thank you, Kamal.
You're welcome.
So thank you, Peter, for all these specifics. And I just for the benefit of those of us who come from the other side, the social sciences, and it's a long time I'm on that side. When you say this is not heuristics that I'm giving you, these are all the exact mathematical relationships. I would very much love to know what is gained and lost when we are focusing on heuristics. But if you could please start with telling us what you mean by heuristic versus mathematical, which is also related to another notion, I think, that you were bringing up, the matter of connection of representations when we go to universal definitions and conceptualization. Thanks.
Yes. In case of mathematical and heuristic, this was related to a particular sense where this kind of derivation was criticized. For example, that the function space were not defined. I was speaking about that fields and so on, but I didn't say what is a function of what. So mathematically, this is bullshit. And because you obtain something at the end, and you define along the process the mathematical notions. And also there is a deep discussion about what use of mathematics and how deep axiomatics should be done in thermodynamics, especially because thermodynamics is, let's say, according to some people are poisoned by mathematics, and according to some other people, there is not enough mathematics in it. And both arguments are correct. And here I just wanted to refer that this usual criticism of the heuristic way of this constructing the entropy production is not really well founded. And what we gain is that if we really clarify the starting conditions and the consequences, then there is a, how to say, straight way to get. So maybe this is not a complete answer.
Okay, thank you very much.